Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is yet another in a series of graphing rational functions, or at least dealing with rational functions. You should have already watched the videos on a review of rational functions from your Algebra 2 course. You should also have watched the video on domains of rational functions and vertical and horizontal asymptotes. And in the last one, which was horizontal asymptotes, we had this kind of piece that we sort of slid under the rug. And that was when we were talking about the degree of the numerator of a rational function versus the degree of the denominator. And the fact that if the degree of the numerator is higher than the degree of the denominator, you do not have a horizontal asymptote. And that is because, as you can see in this case right here, just using the same arguments that I used in the previous video, this, as x gets massive, is approximately, I'm not saying this is exactly, I'm just saying this is approximately, as x gets massive, 3x to the fourth over x cubed. And obviously that doesn't tend to 0, it tends to 3x. So that's a problem. So how do you deal with that? Because we would like it to approach a number, not a variable. But the problem is it won't. It'll always approach a variable expression. Well, this ends up giving us a slant asymptote, or an oblique asymptote, really is what I'd like to call it. So I have a little how-to here. Given a rational function, find the equation of the slant asymptote. And I should, by the way, tell you why it's an equation of the slant asymptote, because we had equations of horizontal asymptotes, right? We could have a horizontal asymptote, let's say y equals 3. And so you have this function that approaches that height as time goes on. Let's just pretend it looks like this. So there's a horizontal asymptote at y equals 3. That is an equation, y equals 3. However, it need not be a horizontal line. You might have an asymptote like this. And what happens in those situations, let's also say that we have a vertical asymptote right there. What happens in those situations is often that on one side, your function approaches that oblique or slant asymptote, and maybe on the other side does the same thing. Okay, so this is, if you zoom out enough, the slant asymptote or oblique asymptote shows the behavior, the long run behavior of your function. These can be very interesting. So for an example, you could have an oblique asymptote that looks like the following. Let's suppose that you have two vertical asymptotes. I'm just making up these things, okay? And then let's pretend as though you have an oblique asymptote that looks like this. So it's a parabola. Then your function might look like the following. It might look like something like this. And then maybe on the other side of this vertical asymptote, it does this and it follows. And same thing, maybe on the other side, maybe it does something like this. I don't know. But as you take a look at this function, the black curve is the actual function that we're looking at. And notice that as we zoom out, that black curve, if you zoom out long enough, it will actually look like that parabola that we had drawn in there. So the oblique or slant asymptotes kind of describe what the look of the function is over the long haul. But how do you find those? That's usually the big question. How do you find those oblique or slant asymptotes? And oblique or slant asymptotes to me mean the same thing. Actually, slant asymptotes are a little more restrictive because they're usually for lines. Oblique asymptotes could give you something like that parabola. Anyhow, how do you do it? Well, you only need to find them if the degree of the numerator is greater than the degree of the denominator. And if you have them, then perform long division. That's this right here. So reaching back into your bag of tricks from when you were in arithmetic, basically, right? So you do long division, and the quotient is the slant or oblique asymptote. This probably requires a little explanation because a lot of people don't recall what a quotient is. A quotient is this. If I give you a numerator and a denominator, so that would be a dividend and a divisor is what we'd call that. You would do the long division and you would get some function, and we'll call that function Q for quotient. But you will also get a remainder, and that will be left over the divisor. You have done this for years. For example, if you had, let's say you had the number 25 and you want to divide 6 into that. Okay. Well, 6 doesn't go into 2. So then you scoot over and you say, well, how many times does 6 go into 25? Oh, that's easy. 6 goes into 25 4 times. And then you take that 4 and multiply by 6 and you get 24. And you say, great, I'm going to subtract that. 25 minus 24 is 1. Well, this means that if you had 25 and you divided by 6, it would be the quotient 4 plus the remainder, which is 1, over the divisor, which is 6. 4 plus 1/6, or 4 1/6. So this is kind of the main idea of how you could do the same thing if you have polynomials rather than just constants. So let's do this with polynomials instead of constants. We have a dividend of 3x to the 4th. You need placeholders, by the way, so for every power that's missing. So we don't have an x cubed, so you want to put in here plus 0 x cubes. We don't have an x squared, so you have plus 0 x squared. We have a negative 2x, and then we have a positive 1. And into that dividend, you're going to try to bring in the divisor, x cubed plus 8x minus 3. Technically, the divisor, you don't need placeholders. So then you ask, just like you would in standard good old arithmetic, how many times does x cubed go into 3x to the 4th? You could do that arithmetic, or that algebra, off to the side. I'll do it in blue. I'm asking, how many times does x cubed go into 3x to the 4th? Well, that is a simple algebra problem. It's just 3x. So I'm saying it goes in 3x times. I'll stack it in the x column, 3x. And then you get to check your work. 3x times x cubed is a 3x to the 4th. Then you do the next multiplication. 3x times 8x is a 24x squared. So I'll put this plus 24x squared. I just put that in the x squared column. And then you say, okay, well then 3x times negative 3, that's a negative 9x. Again, in the x column for that. And just like you would in arithmetic, you're going to subtract that entire statement. 3x to the 4th minus 3x to the 4th, they cancel by design. 0x cubed minus nothing, still 0. 0x squared minus 24x squared is a negative 24x squared. And negative 2x minus a negative 9x, or plus 9x, is a positive 7x. And then you ask, how many times does x cubed go into that number? If it's a fraction, as far as a rational function where the denominator is x, then it doesn't go in nicely. And I'm telling you right now, it doesn't go in nicely because a negative 24x squared, x cubed does not cancel nicely into that. Not like in the first case, x cubed totally canceled into x to the 4th nicely. But x cubed does not go into x squared nicely. So we are done. The quotient in this case is 3x. I don't care about the remainder, but I'm actually going to write the remainder anyway just to showcase something. The remainder is a negative 24x squared plus 7x plus 1. Normally you wouldn't write this, so let me repeat that. Normally you would not write that. I'm writing this to showcase something. And remember, it's over divisor. Divisor is x cubed plus 8x minus 3. Now, as x gets massive, this is why I'm justifying why the slant asymptote is actually 3x. As x gets huge, that remainder over divisor, because the power in the denominator is greater than the power in the numerator, that will tend to 0. That's just because as x gets huge, the denominator is more powerful. This will act like a negative 24 over x, which will tend to 0 as x gets massive. So really, this piece right here is the only survivor as x gets massive. And so the slant asymptote of that function h of x is 3x. That is the guideline to graphing as x gets huge. So the slant asymptote, let me write that down, is y equals 3x. It's super helpful for graphing because then you know when you graph your function in the long run, it will behave like y equals 3x. Let me use green for that. It'll behave like this line. In the middle run, it won't behave like that line, but in the long run, it will. So your graph might look something, let's just pretend, like this. In the long run, that blue curve, if you zoom out enough, will look like y equals 3x. And that's why the slant asymptote is so important. So again, guideline is, if you're given a rational function and asked to find the slant asymptote, as long as the degree of the numerator is strictly greater than the degree of the denominator, perform long division, and that quotient ends up being the slant or oblique asymptote. It's a slant asymptote if it's a linear function, it's oblique otherwise.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.